Chapter 19, second part of 2, and we're going to kind of talk about all these toxins that can be in our body, how our body gets rid of them, why some people get rid of toxins easier than others, and really how do we evaluate what's toxic to us. Anyway, scientists, of course, use live laboratory animals, which is, of course, in itself controversial. This is called an epidemiological study. And what we do is we can use everything from mice to rabbits to monkeys in order to do this, among other things too. And what we do is estimate the level of toxicity of chemicals, but they do have limitations because quite honestly those creatures are not the same as us. They haven't had the same experiences either. Maybe they've been exposed, or we've been exposed rather, to many different types of chemicals, which causes a synergistic reaction. Many health scientists do call for much greater emphasis on pollution prevention to help reduce our exposure to potentially harmful chemicals. So let's not get it out there in the first place. Regardless, toxicity, that's the study of harmful effects. A couple different things that really come into play with whether they're going to be, or how they're rather going to affect us. Dose is how much you take, the dose of substance. Hey, if you take 2 aspirin, obviously that's your dose. Maybe they're 500 milligrams each or 300 milligrams each, so that's 600 milligrams in that case. That's your dose. Age actually comes into play too. Generally very young, developing fetuses even included, and babies are very prone to very low levels of toxicity because their organs are still developing. Your genetic makeup, your multiple chemical sensitivity, which is also called the MCS, meaning how do you react when you have many different chemicals that are affecting you. The solubility of the toxin, whether it be fat soluble or water soluble. Remember, water soluble can actually dissolve in our body, and our body can flush it much easier than fat soluble. Fat soluble substances tend to be those that bioaccumulate into our fatty tissue, and they stay with us a long time. The reason they're so dangerous is because, particularly if a mother's pregnant, they can pass those toxic substances like mercury or PCBs then on to their offspring. Persistence, that's how long it stays in the environment, of course, or even in our body. And of course, biomagnification deals with the food web or food chain. How much does it get increased from one tropic level? Other real important factors with how these chemicals are going to affect us is their effect. It's called, there's response effect. There's something called acute effect. That is immediate or rapid. If the people of Chernobyl actually got exposed immediately to the chemicals of radiation leaking out, they got a very quick reaction. Chronic effect is something that's very permanent or very long lasting, generally over a lot of time. Generally exposure, for example, to lead. If you're a person that lives in an older house that has lead pipes or lead soldering on your pipes, you're getting very slow, long-lasting, chronic effect of those toxins. Here's a couple factors that really come into play with how they're going to affect you. And of course, we can do a lot of computer modeling with this, but it's really hard to tell. And again, a lot of these are synergistic. They come together and make things worse. Air pollutant levels, again, we know if we're in urban areas, we're going to have a higher incidence of lung, whether it be lung problems, it would be asthma or emphysema or things like that. Water pollutant levels is going to vary, and these can all come together too. Soil dust levels are going to affect us. Those are particulates that are in our atmosphere. Food and pesticide levels. Again, remember, things that can absorb pesticides very easily tend to be very bad for us, like grapes. Red peppers tend to absorb those pollutants really easily too, and then we eat those. Your nutritional health, if you're in great shape and your body's working fine, it's probably not going to affect you quite as much. Your overall health in general. Your lifestyle, your personal habits. If you're a person who smokes, obviously, if you drink a lot too, it's double negative, very bad effects on you. Your genetic predisposition is going to come into play with how your body relates or processes these toxins. Your lung, your intestine, skin absorption rates, and even things like your metabolism. These all are factors that come into play with how your body is going to be affected by different levels of. A little case study. We need to protect kids from toxic chemicals, of course. What scientists have actually done is analysis of umbilical cords. What they're doing with that is, of course, the umbilical cord is connected to the placenta, which is connected to the mother. They're looking at the toxins that are passed from mother onto offspring. And of course, like in the Great Lakes region, we worry about eating fish, things like mercury and PCBs in there, because they can actually bioaccumulate in our body and then be passed on to the fetus and cause fetal developmental concerns. It's well known that there's about 180 chemicals found in the umbilical cord that can actually cause cancers in humans or animals. So those poor kids could actually start developing cancers before they're even born. Infants and children are more susceptible to things, again, because they have a less developed immune system. Their body's detox system is not quite processing yet, so they can't really get rid of it. Fetal exposure may increase, of course, risk of autism, asthma, and even learning to. There's a couple ways of looking at and figuring out the toxicity of things. First of all, again, we can use mice and rats. Their systems are very similar to humans. They're not exactly us. They're very small. They reproduce rapidly, obviously, which is quite different from us. What we use is something called an LD50 model. This is also called, it's lethal dose 50. What that means is it's going to kill 50% of a population within this dose curve. There's also called ED50. So it's very similar to this, just a different acronym. So it's a dose response curve, and there's two ways of looking at it. There's a non-threshold response curve, and there's a threshold dose response model of that. This is an LD50. Now keep in mind with LD50, what it is we take a look at a toxin. So there's a dose on the bottom. Maybe we have 2 milligrams, 4 milligrams, 6 milligrams of something. You can even think about this as aspirin. And I'm using that, or Tylenol, because that's something that everybody uses. What happens is we give, let's say we have a bunch of mice, for example. Let's say we have 100 mice. Well, what happens is we give them the dose, and what happens is the percentage of population killed by that dose goes up and up and up. So, for example, if we have 4 milligrams of Tylenol that we're giving these mice, at this level, we have maybe about 5 of those mice are killed. The percentage, I should say, about 5% of the mice are killed. Then what happens is it goes up, about 25% of the mice are killed when they're at about 6 milligrams, for example. And then what happens is when we get to 50% of the population killed, that is our lethal dose 50. So 50% of those mice are killed. And that's at roughly about 6.8 milligrams. Let's just say we're using that hypothetical unit. So what they'll do is drug companies actually use this to try to figure out what the dose is that people can take. Now the problem is we've got to translate this to mice into humans. And of course our body systems are different. That's a huge limitation. However, it's actually a pretty good model, and it's arguably better than just giving it to humans in the first place. What they would do in the medicine world is then give doses like this starting out very low to human populations and see how it translates. So what this means is, of course, we would never want to kill 50% of our population. So maybe we'd stick into the 2 milligram, maybe up to 3 milligram level right here, and that's a safe zone for us to take medicine. We don't want to go above there. It's kind of the idea too with ibuprofen, for example. They tell you to take no more than 6 and 24 hours, because otherwise what happens is you're probably going to get in this range and beyond where it starts killing people because it's safe for our body. Now there's two ways of looking at charts like this. There's non-threshold and threshold. Now the way of looking at these models, non-threshold, what happens is it's kind of like this linear curve right here. As soon as you take one ibuprofen, for example, it starts affecting you. However, if you have a threshold level, what happens is, it's kind of like this chart in here a little bit, is you can take 1 ibuprofen, you can take 2 ibuprofen. It really doesn't affect you because you've built up a threshold or a tolerance to this. So what happens is not till you get it right about here does it really start affecting you or a population in that regard. So think of threshold kind of like a tolerance, where you've built up a threshold toward really doesn't affect you till a certain point. Now again, we can use live animals and non-animal tests to estimate toxicity. The more humane methods using animals is we could replace animals with other models like computers, but it's not the same. It's not us. We could use tissue culture in individual animal cells. So nowadays, of course, with being able to clone animal cells and things, we could actually expose them in a lab situation. But again, it's not the same. We could use chicken egg membranes also with this too, which are very sensitive to toxins, and it kind of is like this, but not the same. So the big question, what are the effects of mixtures of potentially toxic chemicals? So as that chart showed you before, living in an urban area like we do, not only do we have water pollution potential, but we have air pollution potential. We're taking medicines. These are all synergistic effects where two or more things come together and make the effect. How does that really affect us? There are a lot of case reports, a lot of epidemiological studies on these things. The problem is a lot of times too few people test it. I'm not sure about you, but before I take a medicine, I want about 1 million people taking it before me to make sure there's no terrible side effects. And keep in mind, it's generally about 10 years before a new medicine actually comes out on the market. So it's real long. It can be, results could be linked to different chemicals, maybe not used. There's new hazards involved with these chemicals. A lot of these chemicals that they're trying to come out with, like medicines, there's too many side effects, too many other hazards. We're going to get into it a little bit more in the next chapter, which is on air pollution, indoor air pollutants. But just sitting in your house, just sitting in school, believe it or not, you're getting exposed to a lot of chemicals too. So this is another consideration. So you may take ibuprofen for a headache. The reason you might be getting a headache is because you're breathing something in the classroom or in the school or home or something like that, which could be eliminated in the first down the road. So trace level of toxic chemicals, are they harmful? There's different ways of looking at that. Really insufficient data for most chemicals. The problem is, and I'll show you a stat in a second, but the EPA is way behind the 8 ball on this. Haven't tested a lot of them. We're all exposed to toxic chemicals. Trace amounts, maybe those are all coming together doing bad things. It could be antagonistic where they're actually not doing bad things too. There is a difference between increasing dangers and better testing too. Those dangers, unfortunately. So here we are, only 2% of the 100,000 chemicals that have been adequately tested in the United States right now. About 99.5% of chemicals used in the United States are not supervised by the government. So quite honestly, it's relatively easy for companies to come out with new chemicals and they're not tested, so we don't know how they're going to affect. The precautionary principle, obviously, which I've said over and over and over again, let's just not do it in the first place and we won't have to worry about it. In 2000, we had a global treaty to ban or phase out the dirty dozen persistent organic pollutants, which we talked about before. Those are the ones that tend to be on, like fruits and vegetables. DET is an example of this. Very persistent in our environment. We want to get rid of. 3M company, which actually is based up in Minneapolis, has done an excellent job between 1975 and 2008. They actually prevented more than 1.5 million tons of pollutants from reaching the environment. So they really revamped their companies. They're not letting those toxins out in the first place. That is the precautionary principle big time. It's kind of the polluter pays kind of attitude where if you pollute, you need to pay for it. You pay the government, for example, and employees are actually rewarded for keeping the environment clean. Model. We can reduce the risk we face by becoming informed, thinking critically, of course, which is why you're taking this class. Careful decisions. The reality with risk, back to what we started with, is if you're poor, if you're malnourished, in that disease cycle just keeps going because you don't have adequate medicine. What happens is we get about 11 million annual deaths. That is terrible. If you smoke, about 6 million people die annually because of smoking. It is terrible. Pneumonia and flu. About 3.2 million people die annually from that. And of course, now we've got a vaccination for the flu. So maybe if we just got that out more, we'd save so many people. Pollution alone, 3.2 million people. And then we get into AIDS, diarrhea, tuberculosis, which are more transmittable diseases. Millions of people, unfortunately. Lack of adequate sanitation facilities, about 2.6 million people die from that annually. That's 37%. A lot of people don't even have enough fuel for heating and cooking, about 2 billion people, those poor people in the world too. And of course, you've got to give it to our perspective. We're very lucky. A lot of people don't even have proper amounts of electricity, about 2 billion people out of the 7 billion people in the world, by the way. Adequate health care, about 1.1 billion people don't have adequate health care, and it just goes on from there. Even clean drinking water, about 880 million people don't have clean. Terrible. That's why they get sick. So poverty, really the root evil of all of this. It's the greatest health risk by far, so it's terrible. It's a catch-22. These people are very poor, which leads to the fact that they don't have clean drinking water. They don't have proper adequate food. They're very malnourished. Being born male, of course, because us males like to take a little bit more risks, and we tend to die earlier as a result of it. Lifestyle choices come into play with this, where people overeat, they smoke, that cultural lifestyle too makes a big difference. The job too. Smoking, the last thing we'll talk about, most preventable major cause of suffering and premature death. Smoking has killed about 100 million people during the 20th century. It could be linked to increased dementia. It could be linked to Alzheimer's disease. The problem is nicotine, as we know, is an incredibly addictive drug. In other countries, of course, on packs of cigarettes, it basically says you're going to die from doing this. In the United States, we just don't do that. Smoke is actually a huge issue too because you're not getting it filtered. People who work in bars, for example, back when they allowed smoking in bars in the state, what happened was they would die from just getting that passive smoke. How do we reduce smoking? Maybe tax even more, although it is taxed pretty heavy. I'm not sure how much it is for a pack of cigarettes, but it's really high. Classify, regulate nicotine as something toxic, obviously. Ban smoking in public places. Of course, many states have done that already, including ours. And of course, educating like this about it too. All right, that's Chapter 19 with risk and toxicology, and that'll wrap it up.